Okay. Now, in the previous lecture, we stated Burnside's lemma, which is the following. So, given a finite set, let's say Y, and a subgroup G of the symmetric group Sy of Y, then recall that fix of pi is the set of all elements that are fixed by the permutation pi. And the cardinality of x of pi is clearly the number of cycles of length 1 in permutation pi, right? Now, the lemma says that if y mod g denote the set of orbits of g. Okay, so what is the orbit of a group acting on a set? Let's say y. So when you look at the the g equivalent classes, right? So when you have the group acting on the set, you get a partition into equivalence classes, because the G equivalence is an equivalence relation, and these equivalence classes are called the orbits. Okay, so the elements which are taken by the action of a group, like if I take one element, it is going to a subset of the elements, and these subsets form an equivalence class, and that is an orbit, and so we get this orbit. So if y mod g denote the set of orbits of g, then the number of orbits is given by the formula 1 by the order of g, summation over all permutations in g, cardinality of the fix of pi. So the average number of elements of y fixed by the permutations in g is actually equal to the number of orbits of G, acting on the set Y. Okay, so that is Burnside's lemma. Now let's see how to let us look at an example. So let's say that Y is a set 1, 2, 3, 4, and G is is the group with the identity 1, 2, 3, and 4. Then 1, 2, 3, 4. 1, 3, 2, 4, and 1, 4, 2, 3. Right? J and G dash is the group again with identity 1, 2, then 3 and 4. Then 1 by itself, 2 itself, 3, 4. Then 1, 2, and 3, 4. So as abstract groups, they are isomorphic. Both are isomorphic to Z2 cross Z2. But as you can see, as we observed earlier, the action will be different because the cycle structures are different. So the number of orbits of G is given by 1 by 4. The cardinality of G is 4 times. Look at the the elements fixed by each of these. You will see that you will get 4 plus 0 plus 0 plus 0, right, for the action of G. And on the other hand, the number of orbits of G dash is 1 by 4 into 4 plus 2 plus 2 plus 0, because in the cycles 3 comma like 1 2 1 comma 2 3 and 4, the two elements are fixed. Then 1 2 3 comma 4, two elements are fixed again, right? And therefore I get 4 plus 2 plus 2, right? Of course, identity fixes all the elements, which is 4. So the number of orbits of G and G dash are different. For example, in the case of G, you get only one orbit, and in the case of G dash, you get two orbits. Okay. Now let us try to prove Burnside's lemma. Now, for any element of Y, let us look at the set of all permutations which fix Y, right? So which is called the stabilizer subgroup of G, denoted by G sub Y. Okay, so G sub Y is the set of all permutations that are that fix the element y, right? So pi dot y is equal to y. Then to calculate this sum, right? 1 by mod g summation pi belongs to the cardinality of fixed pi. So let us try to sum over all elements of g cardinality of fixed pi, right? Now what is this? So this is sum over all permutations, sum over all the elements in y, right? So so you want to count, right? We count the elements in y, just that pi dot y is equal to y, right? That is precisely the cardinality of fixed pi, right? So the elements which are fixed by pi, right? That cardinality can be obtained by summation y belongs to y, where pi is fixing y 1, right? So this will be the same. But now I can change the order because I can as well count for each element how many permutations fix this. So I can write it as summation y belongs to y, summation overall permutations in G, where y is fixed by pi. Right? So again, but what is this, right? So what is this term, right? Now that is precisely the number of elements, right? Or number of permutations which fix the element y, right? Which is cardinality of gy. Right? So which is the stabilizer subgroup, right? So summation overall y belongs to y, cardinality of gy. Now let us see. Can we look at cardinality of gy in another way, right? So when we look at the action of the group, the elements in the orbit, let's say gy. So I denote by gy the orbit of y, right? Because so what are basically the orbits? So so if I take an element and look at all the other elements to which this element is mapped by elements of G. So this form the orbit of Y. Right? So therefore, it makes sense to denote it by G Y or G dot Y. So now, so elements in the orbit Gy of Y occurs the same number of times in the multiset pi dot y, set of all permutations pi dot y for pi in G. So why is that? Because so how do you prove this? So if you have the following three easy results, like two left cosets are either equal or disjoint, this is something I asked you to go through or prove. Then another easy result that we can show is that two orbits are either the same or disjoint. Okay. Now the number of left cosets of a subgroup, right, is the cardinality of the orbit of y, right? So stabilizer of gy is the cardinality of the orbit of y. How many elements are there in the orbit? That is the number of left cosets of the subgroup gy. Now, if you prove these three, it will be immediately clear that the elements in the orbit occurs exactly cardinality of gy times. So this will give you the identity that the cardinality of gy is actually equal to the number of elements in G by the number of elements in the orbit of y. Okay. So, so once you have this, we can just substitute. So we get 1 by order of g summation fixed pi is equal to 1 by order of g summation y belongs to y, which and it was g sub y, cardinality of g sub y, but that is equal to order of g by order of gy, right? Now what is this? So we can cancel order of g because that is fixed. So therefore I get summation 1 by order of g dot y. Now how many times this particular term occurs in this sum, right? So for every element in the orbit of y, right? So the corresponding term will be 1 by cardinality of gy because elements in the orbit stay together, right? Under the action of the group, the elements in that orbit are taken to the other elements in the same orbit. It doesn't go out of it. So therefore, you will see that exactly the number of elements in the orbit, that many times the term 1 by cardinality of gy occurs. So which means that the contribution of each orbit will be exactly 1, right? Because each orbit has exactly that many elements. That many times this term 1 by order of gy comes. So therefore, this is actually counting the number of orbits. The contribution of each orbit is exactly 1. So therefore, it counts the number of orbits in the action of g on y. So that is what we wanted to prove, right? The cardinality of y mod g is actually equal to 1 by cardinality of g summation fixed y, right? Cardinality of so so that is the Burnside's lemma. Okay. So now, yeah. So here I think I need to write the cardinality of y. Yeah. So that is the Burnside's lemma. Now let us look at an example. So let us look at the sixth cycle. Let us say H, which for hexagons or something, right? Sixth cycle H, whose vertices we want to color using n colors. So you are looking at a regular hexagon where all the sides are equal. So so that there is the symmetry. Okay. Now, so we want to color the vertices using a set of n colors. Now, we say that two colorings are same if one can be obtained from the other by rotation, right? So if I can just rotate the regular or hexagon so that the colorings remain in the position, and then I rotate it, then I get other colorings, right? So these colorings are all considered equivalent, right? Basically, I don't distinguish between coloring obtained by just the rotation of this object. Now, how many inequivalent colorings are there under this? How do you use this? So we want to find the cardinality of fixed phi, and then we get the formula, right? So let us look at the set of all colorings of the hexagon using, let's say, n colors, right? So we look at the set of all colorings. That is our set y, right? We are going to apply the group action on this coloring. So G be the group of permutations of C that permute the color cyclically. So basically the rotations, right? So we can see that since there are 6 vertices, you have exactly 6 rotations, including the identity, right? And you will see that this is actually isomorphic to Z6. Now, of course, these permutations, the rotation, so the subgroup of all rotations can be generated by a single element. You just rotate once, and then that rotation you can apply that to itself again. So if you take this single rotation forward, like one going two going to three, etc., right? And you apply it again and again. Like for example, if it is sigma, then sigma square, sigma cube, etc., you will get all the elements in the group. So it is generated by the single element. Okay, something that we need to we will use maybe. So now let us look at a coloring of the vertices, right? So let's say R G Y B B Y B B W, right? So red, green, yellow, blue, and white. Now once I rotate this, what happens? I can get, for example, red going to green, green going to yellow, yellow going to blue, blue going to blue, and blue going to white, and white going to red, right? So I will get WRG, YBB. Similarly, I get BWR, GYB, etc. by rotations. Right? So I can rotate and get this kind of colorings, right? Where I assume that one is now given the color W, right? After this one rotation, I will get one will be given the color W, right? So W goes here, and similarly red goes to 2, etc. Okay, now the orbits of the group G correspond to the equivalent coloring, right? So we want to count the number of orbits because we want the inequivalent coloring, right? So all the elements in the same orbit are basically equivalent. So what we are seeing here is that these colorings are all equivalent, right? Because this is actually obtained from this by just rotation. This can be obtained by rotation, etc. Therefore, elements in this orbit of this coloring are all equivalent. So we want to find how many such orbits are there so that we will get the number of inequivalent color. Now, what is that? So the cardinality of the orbit of the action of G on C is mod C mod G, the cardinality of C mod G, which by Burnside's lemma is 1 by order of G, summation over all the permutations in G, cardinality of fix of phi, right? Now, if sigma is a generator of the group G, we have the following cases, right? So we have either identity, sigma square, right? Sigma cube, sigma raised to 3, sigma raised to 4, sigma raised to 5, etc. Right? So these are the generators. So let us look at each case. Now, if you are looking at the identity of G, then all the colorings are fixed by pi, right? Because it doesn't do anything, so everything is fixed. So all the n raised to 6 colorings, because for every vertex I have n choices. So all the n raised to 6 colorings of the hexagon are all fixed by pi, right? The identity. So the identity permutation is written like this: 1, 2, 3, 4, 5, and 6. Each one is a cycle. Now, on the other hand, suppose we have the generator, let's say sigma, right? So, which is the rotation by ones: 1, 2, 3, 1 going to 2, 2 going to 3, 3 going to 4, 4 going to 5, and 5 going to 6, and 6 going to 1, right? So, if sigma is the generator, then which kind of coloring sigma fixes, right? See, because it is rotating, the colors in the cyclic fashion, the two colorings are equal only if all the colors are the same, because the colorings basically move around in circle, right? And if I want these two colorings to be the same, I want all the colors in each of the vertex to be the same. Now if each vertex gets the same color, then since I have n colors, I have n different colorings possible, right? Where all the vertices get the same color. So sigma, for example, right, gives exactly n such coloring. Now, what if you look at the sigma inverse, which is the rotation in the backward rotation, right? So 1 going to 6, 6 going to 5, 5 going to 4, 4 going to 3, and 3 going to 2, and 2 going to 1, right? So that sigma inverse again the same, right? So if I just rotate by 1 all the way backwards, again I want all the vertices getting the same color, otherwise the coloring will not be fixed by pi. So for each of these two, I get n such coloring, right? Now, what if pi is sigma square or sigma raised to 4? Then what are these permutations? If sigma is this, then you can verify that sigma square is this permutation: 1, 3, 5, and 2, 4, 6. Right? Now, what is this permutation like? For example, right? 1 going to 3, 3 going to 5, and 5 going to 1, right? Similarly, 2 going to 4, 4 going to 6, and 6 going to 2. Right? So, because sigma square, or in our case, is of this form, if the colorings of these alternate elements, right, are the same, right, then such colorings are fixed by pi, because if I move twice, I just need to get the same color, right? And similarly, for each element, if it moves exactly twice, right, in forward, then that color is the same, then the coloring is okay. So therefore, such colorings will be all fixed by sigma square. But how many are there? Well, I can choose any two colorings for the first two elements. Then we know that the remaining must be all based on this. So therefore, I have n into n square possible colorings, and in n square of these colorings, this sigma square will be fixing each of them. And similarly, sigma raised to 4, which is 153 and 264, will also be fixing such coloring, right? So therefore, n square colorings will be fixed by sigma square and sigma raised to 4, right, each. Now, if pi is sigma cube, then sigma cube is precisely 1, 4, 2, 5, and 3, 6. Therefore, the colorings of the form, like the first three are the same, right? Then, no, first three is fixed. Once you fix the first three, then the remaining three are the same, right? So therefore, I have three choices, right? N into n into n, n cube colorings are there. And these n cube colorings will be fixed by permutations of the form sigma cube, right? Permutation sigma cube. So this covers all possible elements, right? All the 6 elements in the group. So therefore, we can now apply Burnside's lemma, right? So let us do 1 by 6 into, right, 1 by 6 into n raised to 6 colorings fixed by the identity, n raised to 3 coloring fixed by sigma cube, right? Then n square coloring fixed by each of sigma square and sigma raised to 4, and n coloring fixed by each of sigma and sigma inverse, right? So this is the number of inequivalent colorings. So if we are using exactly n colors, we get this. If I am using only one color, what you will get? 1 plus 1 plus 2 plus 2 by 6, which is 1. Right? And for 2, you will see whatever it is. So this is something that we can do, right, by using Burnside's lemma. But now let us observe something else. Okay. So if you look at if you look at this this count, right, that we have obtained here, we have 1 by 6 into, right, n raised to 6 plus n raised to 3 plus 2n square plus 2n. So let us see what is the exponent of n raised to 6 here. Right? So n raised to 6 comes from the identity of G, and you will see that the identity has exactly 6 cycles in its cycle representation, right? So the identity permutation has exactly 6 cycles, 6 one cycles. Right? Now, what about this 2n, right? So the exponent of n is 1, right? Now, how many cycles are there? For example, in sigma, right? Sigma has only one cycle, right? Which is with all the 6 elements, there is one cycle. Sigma inverse also has only one. So you will see that the number of cycles in sigma here, for example, is the exponent of n here, right, in the count. For each permutation, you can verify that it is the case. For example, when you are looking at the sigma square or sigma raised to 4, sigma square has two cycles. So the exponent is 2 for n, right, n raised to 2. Sigma raised to 4 also exactly the same. And sigma cube has exactly 3 cycles, 1, 2, 2, 5, and 3, 6. And therefore, we have exactly sigma, I mean, n cube, right? N cube colorings. Now, why is this? Can you see why? This is something which is kind of easy once you think about it. Because let us say that you're looking at a permutation, and this permutation fixes some colorings, right? Now, if a permutation is fixing the colorings, then look at any cycle of the permutation, right? So if I look at a cycle of the permutation, when you look at the the permutation as the product of cycles, so take any factor, right, which is a cycle. All the elements in this cycle is precisely rotating, right, like by one step, or it forms a cyclic rotation, right. Now, if I have this rotation will be in this cyclic rotation will fix the coloring only if all the elements, that corresponding elements which appear in the rotation, get the same color. So if 1, 3, and 5 are all getting the same color only, the rotation of 1, 3, 5, 1 going to 3, 3 going to 5, and 5 going to 1 will be also preserving the fixing the color, right? So therefore, the permutation will fix the color only if all elements in that particular cycle, right, will get the same color. So therefore, this has exactly n choices because I am using n colors. Now look at the second cycle. The second cycle also the same thing, right? Because all the elements in that cycle must be getting the same color. So again, it has n choices. So that is why the number of cycles determines the power of n, right? Exponent of n. So now it is clear, right? So we can even write it as a theorem now. Okay, so we will go to that. Before that, let me set a homework. The vertices of a 5 cycle, let's say C, is to be colored using K colors, right? Find the number of inequivalent colorings if rotations and reflections of colorings are considered equivalent. Okay, so and once you do this formula, again find the value when K is equal to 7. So that is a homework. Now, this is something that we already observed, that if you look at an encoloring of a finite set X under the action of a group G of the symmetries of X, right? So then the coloring, any coloring is fixed by a permutation, fixed permutation pi, only if all the elements of a cycle of pi get the same color, right? Something we observe. So therefore, the cardinality of fix of pi, right, is precisely n raised to C of pi, where C of pi, is the number of cycles in pi, right? So therefore, by Burnside's lemma, right, we can rewrite, this observation and as follows, right? So if G a group of symmetries of a finite set X, and you are looking at the number of G inequivalent n colorings, right, of the set X, that is given by 1 by cardinality of G, summation pi belongs to G, n raised to C of pi, where C of pi denotes the number of cycles of pi, right? So the proof, I already explained the proof, so I want you to write it down formally, with all the necessary arguments. Okay, so that is the homework for you. Now, so here is a remark. So like if you want to get the the number of colorings with some additional information, like for example, we want to count with respect to the number of occurrences of each color, right? So I want to say that I want to count the number of colorings, inequivalent G inequivalent colorings, where the red color appears 3 times, blue appears 5 times, and green appears 7 times, etc. Right? So I can do that also. Right? This is something which we can do if you put into use the observation that we had in the previous this result, that using the cycle structure of the permutations, we can count this, right? So if you include that also into the formula, then we should be able to clearly tell uh, how many inequivalent colorings are there, where each each color occurs a specified number of times, right? Now, this becomes even more clear when you observe that the permutations, right? The action is by the group G, which is a subset of the symmetric group Sx. So basically, the action is by permutations, right? So now the permutations of a coloring. Suppose I take a coloring and permute them. Whatever your permutation is, it is not going to change the number of times a given color appears, right? So if I look at a coloring and I permute, permute the elements, then I am going to get another coloring where the number of colors of, number of times each color occurs is precisely the same. So the set of all colorings is now can be divided into based on the number of times each color occurs, and that will be like, so the action of the group will be any subgroup that we are looking at, right, will be always restricted to each of these subclasses, right, of the coloring. So with that observation, we should be able to gain more insight. So that is what we are going to prove in Polya's theorem. So so continuing our observation. So let us write the cycle type of a permutation as the n tuple. So we are looking at permutations of n elements, let's say. Then the cycle type of permutation is the type of let's say pi is the n tuple C1, C2, etc. Cn, where Ct is the number of cycles of length t in pi. So this could be like, Ci's could be zeros, right? It is always a non-negative integer, and you can look at some example. But here, so the type of the permutation given by the product of these cycles 1, 3, 7, 2, 4, 5, 10, 9, and 6, 8, 11 is is of type 1, 0, 2, 1, 0, 0, 0, 0, 0, 0, 0, right? So why is that? Well, there is precisely one one cycle. There is no two cycles in this. There are two 3 cycles, 1, 3, 7, and 6, 8, 11. There is one 4 cycle, 2, 4, 5, 10, and there is no other larger cycle. So all these values up to 11 are going to be all zeros. You cannot have anything larger than 11 because the number of elements is 11. Now, once you have such a type, right, so then we can define the cycle indicator monomial, right, of pi given by, let's say, z pi is equal to z1 raised to c1, z2 raised to c2, etc., zn raised to cn. So this tells immediately what is the cycle structure, right? Look at the coefficient of zi, that will be telling the I cycles, right? And not the coefficient, the exponent of zi will tell you the number of I cycles. So given now a group of symmetries, let us define the cycle index polynomial of the group as Zg is equal to Zg of let's say Z1 to Zn, right? It's denoted by Zg of Z1 to Zn is 1 by order of G, summation over all the permutations in G set pi, right? So the sum of all these monomials, right, normalized by the order of G, right? So this is the cycle index polynomial of the group G. So this will be very useful. We will see how this cycle index corresponds to the counting of colorings that we are going to do. So as an example, let's say that we have the 4 cycle X with the vertices A, B, C, D, and look at the group of rotations of the cycle, right? So what is the cycle index polynomial? So Zg is 1 by order of G, which is 4. Now Z1 raised to 4. Why is it Z1 raised to 4? Because there is the identity has exactly 4 cycles, right? Then Z2 raised to 2, because you look at the generator, the square of the generator, you will see that you will have 2 cycles of length 2, so it is Z2 raised to 2. And then you will get 2 times Z4, because you will see that the generator and its inverse are 1 cycles, so are 4 cycles, and there are 2 of them. So that will tell you this this cycle index polynomial is 1 by 4 into z1 raised to 4 plus z2 square plus 2 z4. Okay. Now, as a homework, you can look at the example to find ZH, where H is the rotations and reflections. Okay, so instead of just the rotations, suppose we also allow reflections, then we will see that ZG is actually equal to, ZH will be whatever it is. So find that as a homework. We come to the main theorem that we wanted to prove, which is Polya's theorem. So Poly's theorem, again, as we noted before, what we wanted to do was to count, inequivalent colorings where the number of colorings is given, right? So let X be an n-element set and G be a group of symmetries of X. Now, let us consider a set of colors C, which is R1, R2, etc. Going on, right? Whatever, some set of colors. Now, it could be finite or infinite, but we will just take it to be infinite at the time being. Now, look at the number of inequivalent colorings under the action of G, where the color, let's say Rj, appears exactly Ij times. Okay, so that is denoted by eta of I1, I2, etc. So eta of I1, I2, etc. says that, okay, color R1 appears I1 times, R2 appears I2 times, etc. Rj appears Ij times, right? So look at the such colorings and then see under the action of the how many inequivalent colorings are there. Okay. Now let us define Fg of R1, R2, etc. Right, where the colors are the variables of the Fg. A summation over all the tuples, like I1, I2, etc. Right, eta of I1, I2, etc. R1 raised to I1, R2 raised to I2. So which means that the coefficient of R1 raised to I1, R2 raised to I2, etc. Right, is the number of inequivalent colorings where Rj appears Ij times, and sum over all these, and you will get this polynomial, right? So if you look at, it need not be a polynomial. If C is finite, then it will be a polynomial. If it is not finite, then you will get a power series, right? So you will see that this is basically a generating series, and then we can look at this and the coefficient of this in the series. This time in the series will be precisely the number of such colorings, right? Inequivalent colorings. That is the generation of the that is the definition of the generating function. Then Fg of R1, R2, etc. right, is actually equal to the cycle index Zg, right, of the group, cycle index of the group Zg, where Z set I is substituted by summation R Rj raised to I. Okay, Z I is substituted by summation Rj raised to I. So Zg of R1 plus R2 plus etc. Comma R1 square plus R2 square plus etc. Comma R1 cube plus R3 R2 cube plus etc. Comma etc. Right. So this is what Fg is. So that is what the theorem says. The theorem says that there is a direct relation between the cycle index of the group, right, and the counting of this inequivalent colorings, where the number of colorings are fixed. Number of occurrence of each color is a fixed tuple. So how do you prove this? So to prove this, suppose I1 plus I2 plus etc. is equal to n, right? So of course, when we have only n elements, we cannot use more than n colors, right? So even though the set of colors is infinite, the tuple that we are going to consider, which is going to contribute anything, is going to be always adding to n, which is the cardinality of x. Right. So let I1 plus I2 plus I equal to n, and ij is of course greater than or equal to 0, and the tuple I1, I2, etc. is denoted by I cap. Okay. Now let us say that C I cap denotes the set of all colorings where the number of colors, number of times the color Rj appears is exactly Ij. Right. So as I mentioned before, the permutations can only take such colorings, in the colorings in Ci to again colorings in Ci, because the number of times a color occurs cannot be changed by the permutations. Right. So therefore we can see that the group G, whatever is the symmetric subgroup of the symmetric group we are taking, that group G acts on on this the restricted coloring Ci cap. That is that any permutation pi if you take, and any coloring in Ci cap you take, right? Pi dot f is again an element of Ci cap. And so this action of the restricted action of this group, right? Of each of these permutations, let us say it's denoted by pi I cap, right? So the action of pi on Ci cap is denoted by pi I cap, because pi acts on each of so for each I cap, Ci cap basically gives a partition of all such colorings, and then for each partition, the permutations acts within that partition, right? So that is what we are saying before. So let pi I cap be this particular action of pi on I cap. Now we want to apply Burnside's lemma, so therefore we want to find the cardinality of x of pi I cap. Right? Now how do you find the cardinality of x of I cap? So if you look at any coloring, then this coloring is fixed by pi I cap only if the the cycle structure of pi is such that, right, in any cycle of pi, all the elements get the same color by this coloring f, right? So if you are looking at a coloring f, then all elements of this particular cycle that we are looking at pi should be given the same color by the f, right? Otherwise, when you rotate it, it is going to give a different color, right? So therefore, that will be the same, and of course, the color Rj must appear exactly Ij times, because by definition, right, I in I cap, the action of pi in I cap is going to basically map a set of vertices with the same color to some other set of vertices, right? Exactly the same number. So with this observation, let us define h pi to be the product over all j, r1 raised to j, r2 raised to j plus etc. whole power cj of pi, where cj of pi is the number of j cycles in pi, right? So pi is the permutation which is acting. Then correspondingly, we define h pi to be the the polynomial product r1 raised to j plus r2 raised to j plus etc. whole raised to cj of pi over all possible j, right? Now let us see what happens in this x pi, right? See, when you take the expansion of of this product, right, you will get different monomials, right? That is what the polynomial is, right? It's a sum of monomials. Now, how do we get one of these monomials? So to get a monomial like this, we have to choose some term, right? Let's say some rk raised j from each of the factors, right? So each factor in this product, we have to choose some element, right? So when you expand out, write all these things, or over all the j, you write r1 raised to j plus etc. into r1 raised to j plus etc. cj times. Then like this for j is equal to 1, then j equal to 2, j equal to 3, etc. Right? So we do this for all possible j, and then we get this huge product of different sums, and then a monomial in the whole product is going to come from by choosing some rk raised j from each of these terms, right? Now, what is the choice of rk raised j says? Rk denotes, right? It is a variable which denotes the color rk, right? So rk raised j says that some j cycle, right, is colored with rk, right? All the elements in some j cycle is getting the color rk. Now we know that in this product, right, we have exactly cj times you can take some some ri raised to j, we can choose exactly cj times, right? So therefore choosing a term like of the type rk raised j from every factor says that we are going to color the set x that we are coloring, right, such that every cycle, right, is going to be monochromatic, right? That is what it comes to. So all elements of the cycle get the same color, right? That every cycle is monochromatic. Now the product of these terms will be some monomial, right? Like something like R1 dash J1, R2 dash J2, etc. Where we have used the color RK a number of JK times, right? So this corresponds to whatever monomial we are looking at. Now it follows that the uh, coefficient of this term that we are looking at R1 raised to J1, R2 raised to J2, etc. is actually equal to the number of permutations, number of elements fixed by the permutation pi I cap, right? The action of pi is pi I cap, right? So that by this action, how many? What is the fix of pi I cap? That is precisely the coefficient of R1 raised to J1, R2 raised to J2, etc. So that was the claim that we want to make. The coefficient of R1 raised to J1, R1 raised to, let's say I1, R2 raised to I2, etc. in S pi is fix of pi I cap. Right? Now, so therefore, we can write H pi now as summation over all I cap, right? The cardinality of fix of pi I cap with the with the monomial R1 raised to I1, R2 raised to I2, etc. Right? So this is what S pi is. Right? This is what we just argued, right, before. So now we can apply the result, that is 1 by order of g summation over all pi belongs to g S pi is actually equal to summation over all pi belongs to g product over j, right, which was the H pi was written like this, R1 raised to j plus R2 raised to j plus etc. Cj pi. Now what is this? Right? This is set G of R1 plus R2 plus etc. R1 square plus R2 square plus etc. Uh, yeah. So for substituting for each Ri with R1, like what like yeah. So the first time with R1 plus R2 plus etc. Second time with R1 square plus R2 square plus etc. And going on, right, like this. But now this is summation overall. This is summation overall I cap, right? Like where uh, where uh, where I so writing this in another fashion, we can write is a summation overall I cap 1 by order of g summation overall all the permutations in g cardinality of fix of pi I cap x1 raised to I1 I mean not x1, right, what was that, R1 raised to this is supposed to be R1, R1 raised to I1, R2 raised to I2, etc. Why is this? Uh, because we are substituting for h pi, right, is equal to phi is equal to summation over all I cap, or order of fix of pi I cap, r1 raised to I1, etc. In this identity, right? So by substituting that, we will get this. But now, what is the coefficient of this term in this summation, right? This is by Burnside's lemma. This is precisely the number of orbits of pi I cap, right? That is how the Burnside's lemma was stated. So therefore, this is precisely the number of inequivalent colorings using color Rj total of Ij times, right? So that is what the coefficient of the monomial means. So this is what we wanted to prove, right? So we proved Polya's theorem by as an application of Burnside's lemma. Okay, so what we proved is that the number of inequivalent colorings, right, where the number of times the color Ri occurs is given by the tuple I1, I2, etc. is obtained uh, by obtained by looking at the cycle index polynomial of the group G, right, Zg, and for the variable for the variable Zi, I replace it by summation Rj raised to I, right? So this will give you the uh, the generating function of this kind of coloring, right? So that is what Polya's theorem is about. So now let us look at some example, right? Go back to this, make sure that you understand the theorem well, and then we can look at the example. So one of the standard examples that you give is that of counting of necklaces. So a necklace of length L is, I think we mentioned this in one of the classes a long time before. It's a circular arrangement of, let's say, colored beads. So we were looking at another type of necklaces that time, where the instead of beads we were using cowrie shells and something like that, which is slightly different in some sense. But for the time being, we have uniform circular beads. So we have a circular arrangement of these beads, and we will assume that when we make the necklace, the distance between so in the circular necklace, the distance between any two is the same, so that you get a regular regular polygon with L vertices, right, as the necklace. Now two necklaces are the same if one can be obtained by a cyclic rotation of the other, right? So this is something that we will assume. This is the group action that we have, the symmetry. Then the number of inequivalent n-colored necklaces. If you are going to color the necklaces, the beads with any of the n colors, it is given by 1 by L summation over all d that divides L, phi of L by d, n raised to d. Okay? So this is the claim. Okay? So the number of inequivalent n-colored necklaces is given by 1 by L, where the length of the necklace is L, summation over all d dividing L, right? So all the divisors of L, phi of L by d. Phi is the Euler function. So L by d is, of course, because d is a divisor, L by d is an integer again. Now for this integer, look at the Euler, the number of numbers less than that and coprime to it, right? So where the GCD of that number and L by d is 1, right? So that is the Euler phi function, which is the coefficient of n raised to d. So this is what we want to prove. How do you go about proving this? So if you want to apply Polya's theorem, we want to look at the cycle index of the group. So let us find the cycle index of the group that we are looking at, right? The group is the group of rotations, right? So for the L cycle. So let us say that our set is the set of elements 1, 2, etc. L is the set of bits, and the group of rotations of the necklace are generated by the permutation, because as we mentioned, the rotations are generated by the single permutation, which is given by 1 going to 2, 2 going to 3, etc. Up to L. So if this is the generator, then the group G is given by 1 comma pi square, etc. pi raised to L minus 1, where pi raised to L is equal to 1, right? Identity. Now, what is the cycle structure for permutations in G? So this is a very interesting example. So can you think of some nice properties of the cycle structures of the permutations in G, right? So if you are looking at the group of rotations, what can you say about the cycle structure? So it turns out that you know if you take any permutation in G, there will be there will be several the number of so there is only one cycle type, cycle of some length, and that will appear many times. Okay, so all the cycles in each of the permutations will have the same length. That is what I wanted to say. So all the permutations will have the same length. So can you think of why? Okay, so or can you prove this is true, right? For every permutation in G, all its cycle lengths will be the same. So if you write any permutation in G as a product of cycles, then all the cycles will have exactly the same length. So prove this. So so why is this? So well, if you look at the rotation and then try to represent it as using some modulo arithmetic, you can easily prove this. And observe that, like, if sigma is pi, where pi is the generator, pi raised to m, then sigma has exactly GCD of m comma l cycles of length l by GCD of m comma l. So this is an even more refined claim. So prove this. Now, once you have this, we can apply Polya's theorem, right? Polya's theorem says that once you have the cycle structure, we can directly apply this, right? So therefore, I have 1 by L summation, m equal to 1 to L, n raised to GCD of m comma L, in equivalent, colored necklaces, right? So this is by Polya's theorem. But what we know is that GCD of m comma L is equal to D if and only if, right? M1 less than or equal to m by D less than or equal to L by D, and GCD of m by D comma L by D is equal to 1. Okay. So using this, we can write this same summation as sum over all the divisors, right? So sum over all the divisors of L, 1 by L summation D dividing L. Now n raised to D, how many times it appears? It appears exactly pi of L by D times, because those many times will be those many numbers will be coprime to uh, uh, coprime to what is that? Coprime to D, right? So therefore we get we can write this as in this form. And now, so this is what we were asked to prove. What was it? Yeah, so this is what we were asked to prove, right? Now, as a further observation, the property of the cycle structure of the permutations in G, we have the cycle indicator, right? Zg of Z1, Z2, etc. Zl is written by 1 over L summation D dividing L, pi of L by D, Z raised to D, ZL by D whole raised to D, right? This again directly follows from the property of the cycle structure, because all the other terms will be disappearing. They will not be here, right? So therefore, we will get exactly this. And but now I can write it also as 1 by L summation D dividing L, phi of D, ZD raised to L by D, because I'm just exchanging D and L by D because they are just divisors. If D is a divisor, L by D is also divisor. So I can write it in either of these forms. So we will see that, like, the connection between ZG and the and this form, right? So it follows that Fg of R1 R2. So we wanted to find out Fg, right? The entire generating function we want to find out. We can write Fg of R1 R2 etc. as 1 by L summation D dividing L phi of D. Then you replace this ZD by the corresponding R1 raised to D plus R2 raised to D plus etc. We said that Zi is replaced by R1 raised to I plus R2 raised to I plus etc. So in this case we have only ZD. So we have R1 raised to D plus R2 raised to D plus etc. whole raised to. So this is how we use Polya's theorem. And here are some homework questions. Show that summation overall D divisors of L, phi of L by D equal to L. And the second question asks you to show that if we allow flipping of necklaces as well as rotations, right? Instead of the just rotations, we also allow flipping or taking mirror images. Find the cycle indicators and the colored necklaces. Okay. So try to solve this question. And the third question is that you want to count the inequivalent colorings of a set of L elements using n colors under the action of the entire the full symmetric group Sx. Then show that if summation I times Ci is equal to L, then the number of permutations in SL, right, with the Ci cycles of length I is given by L factorial divided by 1 raised to C1, C1 factorial, 2 raised to C2, C2 factorial, etc. etc. So these questions are your homework questions. So with that, we wind up the topic on policy. We can do more on this, but let us stop with this for the time being. I will try to give you more questions if you want. There are several interesting questions one can, but at the moment these are your homework questions, and then I will come up with more questions and send you soon.